concentration of your unknown by looking at how the known absorbed and the unknown absorbed. Okay, so this is going to be constant. This is going to be 4 different unknowns. You're going to stick them in your colorimeter. Okay, and if you multiply that by the molar concentration of the known, you get the molar concentration of the unknown. It's Beer's law, and I decided not to. It's in your background information. Okay, so before we talk about calculations, let's talk about the nuts and bolts of getting those molar concentrations. So your instructions are to bring the three solutions you're going to need back to your desk or back to your workstation or whatever. You need a rack with 5 test tubes because 1 is your known and then you have your 4 trials. That makes the 5 test tubes. So here in this one is your known. Okay, we have 2 iron concentrations and your write-up specifically says use the strong iron 3 for your known. So I think your instructions were like 9 mils of this. That's a lot. Okay, 9 mils of this and 1 mil of this for your known. Okay, and I think your instructions are to kind of mix it up. It should turn red for you. For a total of 10 milliliters. And then later on you can calculate the molarity of everything given that 10 milliliter volume. So that's your known. Then your unknowns, you can see that you have a little table thing that goes with those. Okay, so right here it says that for your 4 trials, for your 4 unknowns, in each of them you're going to put 5 mils of this. This is your weak iron. Okay, 5 mils of this in each of those. Okay, the middle column says 2 mils of, this one, this is going to vary. This is actually, I know it's just said SCN minus because that's the only ion we care about. That's your thiocyanate. But it's potassium thiocyanate. The K, just along for the ride. I think we talked about spectator ions, okay? So potassium is just a spectator ion. So this actually is going to vary in each of your trials. There's no time to this. You just kind of mix it up, stir it up good, and then you're going to measure the absorbance, okay? So there's no time thing. I was like, would that mean quick at that? No, okay? And it really goes kind of quick. So basically you're going to have 5 test tubes with liquids that you need to measure the absorbance of. Just remember how you measure the absorbance. On page 77 it talks about you turn on the unit. These are really, you guys don't know how good you got it. These really, they've cut down on some of the time and they just are nicer to work with. So remember there are ports there to plug in your colorimeters and it will automatically see what it is, that it's a colorimeter. Remember it talks about you do have 1 calibration point with water. So if you read item number 6, it says put DI water in it first. Okay, and remember don't fill your cuvette too full because it'll spill into the chamber. Okay, and kind of wipe down the sides. Make sure your ribs are to the edges, not where your light path is going. Notice number 7, it says the wavelength that we want to go to is 470 nanometers. Okay, so make sure you select that. Number 8 talks about calibrating the colorimeter with DI water. Okay, and then step number 9, it's basically a matter of, dumping out you dump out your DI water, and then you go ahead and you start to measure your 5 samples. Okay, so it's really kind of anticlimactic. I'm going to go ahead and get some little squeezy bulbs, because sometimes it's easier to, here's kind of a couple different sizes. Sometimes it's easier to use that pipette to get it in there from your test tube. So that's kind of whatever you think works. So you'll have those 5 absorbances. So let's take a look at the calculations. All right. So the first calculation. Now, when I hand back your graded labs, I think I'm right to say this. Almost nobody is doing it, or I should say everybody is not doing it, writing the labels. You might be a little confused what I mean by labels. On this Prelab, anything that's purple is a label. Okay? Yes. So, and I think I'm going to start doing that because you guys have had me for like a whole semester. This is Chem 2. So yes, label them, right? Because I think that I took off a whole point. One semester, I remember I just had it. I said I'm going to take off 3 points if you don't label it. That's it, 3 out of 10. So anyway, purple is what I'm after. If you're wondering, what does she mean by label? Well, that's what I mean. Okay, so the first one is to get to the molarity of the unknown, and specifically, this is the Fe3+. This is to get to that 9 mils of, okay, and that was the stronger one, right? Oh, wait a minute. What I forgot to tell you, and it's your background information, is we're using 9 mils of that strong iron 3. Here's the deal. The reason we're using that, turn your attention to the thing we're not using much of. That's the SEN-. That actually is your limited reactant, and we're assuming that the amount of that complex that we're really interested in is going to actually be driven by that limited reactant. Okay, and it's kind of a technique of basically dousing it with something and having a smidgen of something, assuming all that smidgen is going to be used up. Actually, calculation 8 looks to see if that assumption is valid. Okay, so this one says, all right, if you want to know how much complex you got, turn your attention to the limited reactant, which is your 1 mil of the thiocyanate. So you use its molarity and its volume, and you divide by the 10 mils. Okay. So probably a better title, and I already posted these, so I won't post them again. But instead of saying molarity of unknown, I probably should have said something like in terms of the complex. That's the FeSCN2+. All right. So that's calculation 1. Calculation 2 then is to get I was trying to say, yeah, these are for your unknowns. The calculation 2, to get the concentration of the iron 3 in your 5 mils, remember this is 5 mils for each of your 4 trials. What is that molar concentration? Okay, and that will be the same for each of your trials. I'm going to go ahead and say this is for the trials. Okay, calculation 3. And this will vary for each because I think you're going 2 mils, 3 mils, 4 mils, and 5 mils, I think, for that SEN-. So for each of your trials, you did have a different amount of the potassium thiocyanate. So calculate the SEN- for each of those. All right, now we use your absorbances. The redness of your solutions that you were getting at that particular wavelength. Okay, so basically you're going to use the absorbance. You're going to use, these numbers are going to be constants. Well, they're constants for me. This is a constant. That's always the same, and that's always the same. Okay, the absorbance of that first trial, the absorbance of that your known, same. The molar concentration of your known, you've got that from calculation 1. Okay, what's going to change to get the molar concentration of each of your unknowns is the absorbance of each of your unknowns. Okay, so that's how you're going to do that. So there'll be 4 calculations. That's your blood red stuff. Calculation 5 is to make 4, count them, 4 ice tables, an ice table for each trial. You can do it. Okay, so ICE stands for initial, change, and equilibrium concentrations. Okay, so you figure you have your initial concentration of your iron 3 from calculation 2, your initial concentration of your thiocyanate, which was different for each of your 4 trials, from calculation 3. No blood red to start with, right? But you got the equilibrium concentration of your complex from your absorbance, and that was calculation 4. All right, so now this is the deal where we can actually do like we've been doing in lecture. Once you have that one equilibrium concentration, you can say, oh, that must be the change in my FeSCN plus 2. Then you can piggyback and go to use stoichiometry, which is just a 1-to-1-to-1 here, to go ahead and get the change in your other 2 species. Notice when you started, you didn't have any product, so that's a plus change, and so it must be a negative change for your reactants. Then, like you've been doing for your homework, to get the equilibrium concentrations, and this won't have any quadratic or anything, right? Those will be real numbers. Basically, you just take the initial, apply the change, and come up with equilibrium concentrations. Then, number 6, you're ready to go ahead and plug those equilibrium concentrations for each of your trials back into your equilibrium constant expression, where it's just the product equilibrium concentration raised to its stoichiometric coefficient, which is 1, divided by each of the reactants raised to their stoichiometric coefficients. So you'll have 4 Kc values. And then that brings us to number 7. Number 7 is just to get the average of those 4 values. So you add them together and divide by 2. Oops, divide by 4. Okay. So I mentioned that we're actually going to see if we were right to say basically all of that 1 mil of SCN minus was used up in that first known. And here's how this goes. It's called calculation 8, and we're checking that original assumption. Notice everything in purple would be very valid titles. One more ice table, turning your attention to the known now. Not your trials, but the known. So this ice table is for your known. So you're going to use that whopping 9 mils of that concentrated iron 3, okay, to get the moles of Fe3+, or the molarity of Fe3+. Molarity of your thiocyanate would be that cute little 1 mil of the 0.00200 molar potassium thiocyanate. Okay, and of course you didn't have any of the complex when you started. Okay, this is the deal where actually now we know the Kc. How do we know the Kc? Because you guys got it in calculation 7, your average Kc. So now we are going to actually end up with having to use a quadratic equation. So if we go with the amount of complex produced is plus x, then we have the amount of SEN minus used is minus x, the amount of Fe3 plus used is minus x. Okay, and you're back to basically at equilibrium, you take that number and apply the change, take that number, apply the change, take that number and apply the change for those 3 equilibrium concentrations, but you're going to have an x. But you also have a Kc. So one last time, your equilibrium constant, but now you know your Kc, like I said, from your average from calculation 7. And so, and actually this says it in your write-ups. It says, how do you prove, well, here's the deal. If that complex concentration, actually you calculated it clear back in calculation 1. Calculation 1 you came up with for your known, how much complex do we have? So we're going to see if that's kind of the same number that you get on your ice table here. Okay? That's the roadmap. Any questions? And I heard it's not a very long lab, so I hope you're not disappointed. The calculations are long. Okay.